Hi, everyone. Welcome. So this week we have our friend Lingyun from the University of North Carolina speaking to us about enhanced diffusivity and skewness of a diffusing tracer in the presence of an oscillating wall. It's a mouthful. So, well, it's all yours.
Okay.
Thanks for coming.
So thank you for coming here. So today I will present the talk about this work. It's about the enhanced diffusivity and skewness of a diffusing tracer in the presence of oscillating wall. So this is a work with Robert Hunt. He is former graduate student in our group. He is a very great experimentalist. He set up a programmable machine for the experiment. And Richard McLaughlin, he is my advisor. And the Hunter Woody is undergraduate student in our group. So in this study, we mainly focus on this type of partial differential equation that is advection diffusion equation. So, but here we only consider time varying shear flow. Okay, so there's a several application of this partial differential equation. First, we can consider that is a model of solute transport. So in this case, T will be the concentration of the tracer. So we can consider such a diffusing tracer advected by the prescribed velocity field.
So
yeah.
To clarify, U is given, yes?
Yes. So we consider the scalar as a passive scalar. So that means we given the velocity field and let it advect the scalar field.
Okay.
Yeah. This is the first application. The second application is it also appeared in the Navier-Stokes equation. We know the three-dimensional Navier-Stokes equation takes this form. And if we assume the velocity field takes this form, it only has the first and the second component, and the third component is zero. And also we have the external force. It takes this form. We only have the first and second component, and the third component is zero. So if we put these answers into the Navier-Stokes equation, we could obtain these equations. So we have an equation for V, and let's check the equation for W. We can see that that is also an advection diffusion equation, and also it has the same form as the one we saw before, right? But the only difference is here, the parameter K is the diffusivity, the molecular diffusivity. However, here, the parameter is the viscosity of the fluid. That's the difference. Another difference is for the in the solute transport problem, we mainly consider the no flux boundary condition. However, for this Navier-Stokes equation, we know if we have rigid boundary, the boundary condition should be usually is the no slip boundary condition. So that's the second difference. But we can see that they have the exactly same Darwin equation. And for this field, people will interested in this question. So will the solution of Navier-Stokes equation converge to the solution of Euler equation as the viscosity vanishes? We know if we set mu, the viscosity to be zero, we obtain the Euler equation. That's why people are interested in this question. So the answer is not necessary. In some cases, the solution may not converge to the solution of Euler equation. However, for this setup, people prove that as the viscosity vanished, we can recover the solution of oil equation. So let's back to this advected diffusion equation. So here I will consider, so let's define the domain of the problem. So here I will consider a transport in a very narrow domain, for example, pipe. So in this case, it has the length of the pipe is much larger than the radius of the pipe. So we can consider approximation for the solution. So first, we can define the cross-sectional average as this. So that is, we take the solution of this equation and compute the integral over the cross-sectional domain. And the next, we can after we compute the cross-sectional average, this becomes a function of x and t only. So we can consider the, we are interested in the distribution of this. So we can use the moment to study that. And this is the classical definition of the moments. We interesting two important moments. The first one is the variance. Why do we interested in that? Because by the homogenization theory, we know the advection diffusion equation can be approximate by a Gaussian distribution at long time. In other words, this equation can be approximated by an effective diffusion equation as t goes to infinity. So here, kappa effective is the effective diffusivity, which is defined as the variance divided by 2t, then let t goes to infinity. So you may ask, what is the application of this approximation? So I think one application is we can use this relation to measure the diffusivity. So let me give you some background. So first, let me ask this question. How can we measure the molecular diffusivity? So our intuitive method is we can use the relation between the mean square displacement and the diffusivity, right? So the variance equals 2 times the molecular diffusivity times t. So we can use this relation to measure the diffusivity. However, this is very hard in practice because we always have some perturbation that will destroy the diffusivity measurement. Let me show you a video. So, okay. Can you see this video?
I can't see it yet.
Okay, great, thank you. So what happened here? That is, in the beaker, that is the.
Yeah, I can see it. Hold on.
Yeah.
But we can't see anything.
Oh, really? Let me share the screen again.
Yeah, I think it shows the application that you're
there we
on.
go. Okay, now we see it. Now we see it.
Yeah.
Perfect.
Oh, okay. So you can see the video now, right? Okay, thank you. So in this beaker, that is the syrup. We know that is very viscous fluid. The viscosity of that fluid is almost 2,000 times larger than water. So any input momentum will dissipate very quickly. And here, what is the so I put some dye inside the syrup. I want to let it diffuse to measure the diffusivity. However, as you say, Okay, so we can clearly see that. So first I should mention that the experiment actually takes more than 10 hours. The video is speed up. We can see that
that was how long? That video took?
10 hours.
10 hours. Okay.
Yeah. So the diffusivity, the molecular diffusivity is very weak. So it usually take probably 1 day for diffusing 2 centimeters. So to get some visible result, we should wait for a very long time. Yeah, and that is a disadvantage to measure the diffusivity by the pure diffusion process. The second disadvantage is there's always small convection in the fluid. So even for such viscous fluid, there's some convection inside it. We can't eliminate that. Okay, so I just want to show that if you want to use the pure diffusion to measure the diffusivity, that's very hard. So one idea proposed by this science paper is we can use the effective diffusivity to measure the molecular diffusivity because the effective diffusivity is a function of kappa. So when there's flow in the pipe, we can measure the effective diffusivity probably just in 5 or 2 minutes. Then we can use the relation to calculate the molecular diffusivity. So that is a very fast and efficient method. Okay, so that is for the variance. And we're also interested in the skewness. So that is higher order moments. And I'd like to introduce this work done by our group. This is also interesting study. That report an interesting phenomenon. If we use the circular pipe, we can see that the distribution of the tracer has this form. We can see it is skewed to the left. And I think if you compute the skewness of this distribution, that should be positive. And that's for the circular pipe. However, if you use the rectangular pipe to transport the solute, you can see that the distribution is skewed to the right. And if you compute the skewness, this time the skewness is negative. So I think that is very interesting. That means if you have some desired distribution in the chemical delivery problem, you can simply control it by choosing suitable geometry of the pipe. And that's why we're interested in studying the skewness in the solute transport problem. Okay, so that is the background of this study. And here, let me describe the setup of this problem. Okay, so this is our experiment setup. So first we have a big tank and we put 2 walls inside the tank. They are parallel. And the front wall is fixed and the back wall is movable. And actually we use a programmable machine to control the movable wall. And we can choose some signal and that will control the motion of the wall. And we're interested in what would be the distribution of the tracer. And actually I can show you a video of this experiment. Okay, so can you see this video? Okay, good, thank you. So we put the tracer right here, and this is the front wall, which is fixed, and you can see this. The things moving at here is the movable wall. So this is the setup of this experiment. Okay, so let's back to the slides. In this problem, the Navier-Stokes equation reduced to this heat equation with prescribed boundary condition. So if we solve that, we can get the velocity field. Okay, so to study the problem, we need some non-dimensionalization. Okay, so after the non-dimensionalization, we obtain this equation, and here we introduce a non-dimensional parameter Schmidt number, so which is defined as the viscosity divided by the diffusivity. And also, because here we consider the periodic input signal, so we also have the dimensionless frequency omega 0. So it connects to the Schmidt number by this relation. So omega 0 equals WO squared times SC. So here, WO is the Ohm's number, which is defined as L. Times square root of omega divided by mu. So suppose the input signal is cosine omega 0 times t, then the solution of this equation takes this form. So this is our velocity field. And by looking at this expression, we can see that if we fix time, then the Ohm's number will uniquely determine the profile of this velocity. That's why it is important. Okay, so that is for the velocity field. Then let's take a look at the advection diffusion equation. So this is the non-dimensionalized equation, and here we introduce the Picklin number, which is defined as the velocity times L divided by the diffusivity. And here the domain is R times omega 0. That means X is a real number, and omega here is Y belong to this closed info, and Z is any real number. Okay, to study the diffusivity and the variance, we can use a technique called the Aris moments. So Aris moments is defined as this. By the integration by parts and divergence theory, we can obtain the governing equation of the Aris moments. Okay, so let's try to solve them. To solve this equation, we need to introduce some notation. So first, we assume the velocity has this Fourier series representation. And here we also introduce phi and lambda. That actually is the eigenvalue and eigenfunction of the Laplace operator. In this simple domain, we have the explicit expression of them. And here we also use the inner product to denote the, we use this angle bracket to denote the inner product. Okay, so to get the effective diffusivity, we just need to solve T0, T1, and T2, because the variance is defined as T2 bar divided by square of T1 bar. So to compute the variance, we need to know the expression of them. Now let's solve them one by one. first, if we set n equals 0, we can solve t0. That's very easy. The solution is trivial, t0 equals 1. If n equals 1, then the governing equation of T1 takes this form. We can also solve it by series expansion. So this is the solution of T1. We can sometimes simplify this equation by introducing the inverse operator. And for this problem, we actually have integral representation of this inverse operator. Okay, now we can solve T2. The governing equation of T2 is this one. We can also use the series expansion to solve T2, and this is the solution. Okay, so once we know T2 and T1, we can compute the effective diffusivity. So we obtain this result. Here we have an interesting observation. That is, if we consider the steady flow with some integration by paths, we could connect the effective diffusivity to the H-1 norm of the shear flow. By the way, so here is the definition of H-1 norm. That you can consider it as, so we first, so this means we have to solve Laplace equation related to U, then take the gradient. Then the L2 norm of that gradient is the H-1 norm of U.
So this delta inverse is just integral operator against probably Green's function.
Oh, yes. Yeah.
Okay.
Or you can understand it in this way. So this is defined as the Laplacian of phi equals U, and of course phi should satisfy some boundary condition. In this case, it should satisfy the no flux boundary condition. Yeah, thank you for the question. Okay, why is the H-1 norm is interesting? Because there's a field called chaotic advection. We know usually we use the variance to measure the degree of mixing. However, if the diffusivity is very weak, or the flow is very strong, in that case, we can assume the diffusivity is 0. When diffusivity is 0, by some calculation, we can show that the variance is constant for a system governed by the advection diffusion equation. That means in such a system, the variance is not a good quantity to measure the degree of mixing. So people propose that we can use H-1 norm to measure the degree of mixing. So that is actually very good measurement, even there's no diffusivity. Then we can see that the effective diffusivity, which is measurement of mixing efficiency in our problem, and that also connect to the H-1 norm of the shear flow. That's why I think this connection is interesting. Okay, so that is for the effective diffusivity. Then let's take a look how the skewness involved in this system. So to compute the skewness, we need to compute T2 and T3 bar. So first, this is the governing equation of T2. So we can also solve it by the series representation. We obtain this. Then we can solve T3 bar, and this is the result. Okay, so once we know T2 and T3, then we can use the definition of skewness to compute it. Okay, so this is the definition. with this definition, we obtain this expression of the skewness. So here we can see that the decay rate, notice that we have square root of t in the denominator. So the skewness actually decay as 1 over square root of t. So if t is large enough, the skewness will converge to 0. And that's why the solution of this equation can be approximated by a symmetric Gaussian function at long time. There's an observation, that is, if we only use a single frequency flow or a flow with a suitable frequency separation, we can show that we can accelerate the decaying rate of the skewness. So in this case, we can see that the decay rate is 1 over square root of t cubed. That is much faster than the one we saw before. Okay, so this observation suggests that we can simply control the frequency components of the flow to control the skewness of the tracer. Okay, so if we put the expression of the shear flow into the expression of the effective diffusivity we derived before, we obtain a very long formula for the effective diffusivity. And here is some study about this quantity. So here we in this plot, we plot the enhanced diffusivity, which is kappa effective minus 1. And we fix the PK number to be 1. And here we vary the Ohm's number and the dimensionless frequency. We are interested in that if we fix the frequency, what kind of parameter could maximize the effective diffusivity. So here the black curve indicates the location of the enhanced diffusivity maximum in the phase space. And the right curve is asymptotic analysis result. Okay. So if we denote the Schmidt number or Ohm's number for reaching the maximum of effective diffusivity as F Schmidt of omega and F Ohmsley of omega respectively, then if omega is large, we can get this result. F Schmidt of omega 0 is around 2.3, and if the frequency is small, we have this result. F Ohmsley of frequency is around 2.5. Okay, so let's take a look at the experimental result. So first, we want to experimentally verify the velocity profile. So here we use a technique called particle tracking velocity measuring. So I can show you a video of, about this technique. Can you see the video? Okay, thank you. So this is a video of PTV technique. In this method, we put many seeding particles into the fluid and use a laser to illuminate those particles. So then we take a bunch of pictures. Each picture indicates the location of the particle. Then we check in those particles so that we can compute the velocity of the particle. And since the particle is very small, so we can assume that the velocity of the particle actually is the velocity of the fluid at that point. So that is the idea of the PTV technique. Okay, so we use the PTV method to measure the velocity, and here's the result. The colored curve is a theoretical prediction of the velocity field, and the black curve are the experimental result. Yeah, what's the question?
So what was the time scale of the last video? Was it
Well, actually, this is a different problem, and the time scale of this is 2 hours actually. Yeah.
So what are the what were the particles inside? So it's particles moving in what fluid, I guess. What particles?
Oh, okay. So from here to here is 0.5 centimeter.
Okay. Okay.
Yeah. So that is very small particle. Yeah. Okay, so from this picture, we know we can experimentally verify the velocity profile. Then we next step is check the distribution of the tracer. So here is the comparison between the Monte-Carlo simulation results and the experimental results. So let me see. Okay, so the second column is the photo from the experiment, and this column is simulation results from the Monte-Carlo method. So we can see that they are very consistent. And here we also compute the cross-sectional average of each photo. I think the red solid line is the result from the experimental data, and the blue dashed line is from the Monte-Carlo simulation. So they match very well. Okay, so next, we want to measure the effective diffusivity from the experiment and compare it to the theoretical value. So we did many trials and 4 different parameters. And here is effective diffusivity measured by the experimental method, and this is the theoretical prediction. So I think the result is good.
So I mean.
Oh yeah, what's the question? Yeah.
I guess I mean, how do you interpret how good is the result? Because I mean, I don't know how much accuracy you guys want.
Oh yeah, so actually there's a column about the relative difference, but seems the table is too large, so it didn't show up. Yeah, so I should say the relative difference, the maximum relative difference is around 50, and the most relative difference is less than 10%. So that's why.
Are you just looking like for order of magnitude sort of equality? I mean, then it looks okay, but I mean, I don't know how close the experimental value should be to the theoretical.
Oh, so
the last column seems to be missing.
Yes. If you compute the relative difference, actually it's this quantity. That is around 0.1. Yeah.
Good enough.
Yeah.
Okay. I believe.
Yeah. Oh yeah. So probably you might curious to what is the meaning of this density? So that actually we have a difficulty in the experiment. So as we saw in this video, we know there has some uncontrollable convection inside the fluid. Then the question is, how can we eliminate this convection? The method we use in our experiment use use linearly stratified fluid. So since the fluid is stratified, so there's only convection in each horizontal plane. So that can much reduce the convection between, I should say the convection in the vertical direction. So we use the salt water to make the stratified fluid, and that the density here is indicates the density of the salt water we used in the stratification. Okay, those are experimental results, and here is simulation results. So this is a top view of the traces distribution. So here, this side is a fixed wall, and this side is a moving wall. Okay, so in this graph, we consider a linear shear flow that equivalent to have infinite viscosity. And there's no diffusivity, so we can say that since the signal is periodic, so after the one period, everything goes back to the original place. However, if we introduce some diffusivity into this system, we can see that after one period, the die is spread. Okay, so how about this panel? So in this panel, there's no diffusivity. However, the viscosity is not infinite. It has finite viscosity. So we can see that we have non-trivial shape of the distribution. And here in this panel, we increase the diffusivity. And we get some interesting pattern of the distribution. And we can see since since the velocity is larger near the moving wall, so we can see that the traces spread more near the upper wall. Okay, so here is a study about the distribution for different parameters. So from the viscosity is decreasing from right to left. So the viscosity is decreasing, and the diffusivity is decreasing from top to bottom. So we can see that if we have a smaller viscosity, the dispersion is more confined near the moving wall boundary. And if the viscosity is larger, the energy could propagate more through the channel. Another interesting observation is that this is a picture at the end of the period, which means since we use the periodic signal, that means the wall will back to the original place after one period. However, we can see that the distribution is not symmetric. It has some non-zero skewness inside the distribution. Okay, so that suggests that then we're interested, can we control the skewness by control the phase of the periodic signal? So here we did a simulation to verify that. So here we use different input signal. The profile is exactly the same. The only difference is they shift by different phase. So for example, here's 0 and here's pi over 4, and this is 2 pi over 4, and this is 3 pi over 4. And here we plot the skewness of the distribution. We can see that they have quite different pattern. For example, in this panel, the skewness is almost negative. However, in this panel, it is positive at halftime and negative at another halftime. So that suggests that we can simply control the skewness of the distribution by control the phase of wall motion. Okay, so that's all about this presentation. Thank you for listening.
So let's thank our speaker really quick. It's got a clapping button, isn't there? There we go. So any questions from the audience? I might have one if no one else.
Okay, yeah.
So how close? So you're in what department? Math or?
Applied math, yeah.
Applied math. Okay. So how closely do you work with experimentalists? I mean, I saw a lot of videos in there. So
yeah, we actually did a lot of experiments. Yeah.
Okay. So what results? I guess you're looking for. What sorts of results? I guess is sort of a question I had. So you want to be able to control something given something else. I think was the point.
So I think the goal is to understand how the quantity, for example, the effective diffusivity depends on the parameter of the system, like how does it depends on the viscosity or even temperature of the system. There's several applications. For example, if we can understand the relation, then we can measure this quantity by measuring the diffusivity.
Okay, so it's like the goal might be to measure, or a more effective way of measuring the diffusivity, yeah?
Yes. Yeah.
Because you were saying that before, I guess the current methods of measuring the diffusivity is to wait 2 or 3 hours. Or how many?
Yeah, that's right.
Yeah. Okay. So it would shorten, I guess.
Yeah, that is one. Yes, one application. And second is very straightforward because I think people will interested in how can we maximize the dispersion. How can we find the efficient mixer? Yeah, that's another motivation of this study.
Okay. So what was I can't remember. So the timescale originally for the for computing the diffusivity was like, I think you said, what was it, 10 hours or something?
Oh yes, yeah.
And so this technique would be comparatively how long, I guess?
Okay, so we can do a simple calculation. We know, for example, salt. I think the diffusivity is around 1.5 times 10 to the negative 5 centimeters square per second. So you can imagine that if you want it to diffuse for 1 centimeter, it definitely take hours.
Yeah, okay.
Yeah. However, if we use this to measure the molecular diffusivity, it will only take probably 2 to 5 minutes, because this time scale is enough to get a good measurement of effective diffusivity. Then you can use the relation to compute this.
Okay, so it's like a good order of magnitude reduction.
Yes. Yeah.
Okay.
Yeah. And actually, this is very popular technique in the biology lab.
So is it commonly accepted to use this technique now, or is it kind of still being like?
Oh, yeah, this is some kind of classical method. Yeah. As you say, the year of this paper is very old.
94, yeah, okay.
Yeah.
So it feels like this is classical.
Yeah.
Okay, cool. So any other questions from the audience? Quiet crowd today. So if not, let's thank our speaker one more time.
Yeah, thank you.
Thank you again for coming and talking. And let me stop the recording really quick.
Mhm.
It was great having you.